Welcome back, students. In the previous lecture we have started with the unit of transmission line. We have gone through the introduction of the transmission line. What are different types of a transmission line? What do you mean by guided media and unguided media? So transmission line is definitely a type of guided media where these electromagnetic waves from source to the destination are transferred through the guided medium. There is another one more type of guided media which we usually use is a waveguide, which is not the point or which is beyond the scope of this particular course. Then we have gone through the different structures like coaxial cable, parallel wire cable, microstrip line, conductor over this conducting sheet, and etc etc. Then we have started with the transmission line parameter, and looking at this diagram we came to the conclusion, or I had told you that the parameters of the transmission line in terms of resistance, conductance, inductance and capacitance are distributed over the line. They are not lumped one. Okay, so this field theory approach should be used in this case instead of circuit theory approach. So we have talked about that in the previous lecture. Let's talk about those things. So first of all, if I have two conductors, okay, if I have two conductor transmission line, so though conductors are having infinite conductivity, there will be a small resistance associated with it, so it will be denoted by R. If I am talking about a conductor and current start flowing through it, there must be inductance associated with it, so this is L. If it is a two wire conducting line separated by air as a dielectric, there must be a capacitance associated with it, and there will be a shunt inductance, shunt conductance. This conductance is not exactly opposite of 1 by R. That means if resistances are here, in this case of a transmission line, G is not equal to 1 by R, or R is not equal to 1 by G. So if this is a two wire transmission line, there will be a certain parameters associated with it. So we are going to see those parameters, the introduction to those parameters in detail. Is it okay? But remember one thing, whenever I am talking about any transmission line basic parameter, they are called as a primary constants of the transmission line. R, L, G, C are called primary constants of the transmission line, and when we will talk about Z0, gamma, alpha, beta, those are called as a secondary constants of the transmission line, which are derived from the primary constant. We are going to see certain numericals based on it also, but right now just try to understand. So the values or the primary constants are R, L, G, C, and units of R, L, G, C are, the unit of R is ohm per meter since it is a distributed parameter. Unit of L is Henry per meter. You already know the unit of inductance is Henry. Unit of capacitance C is Farad per meter, and unit of conductance G is either Siemens per meter or it is mho per meter. So anyways it will be per unit length of the transmission line. So let's talk about those things in detail. I will take you back to this particular thing. It is customary and convenient to describe a transmission line in terms of its line parameters. So what are those line parameters? They are called primary constant, which are its resistance per unit length R. Resistance per unit length means its unit is ohm per meter. Inductance per unit length L, that is Henry per meter. Conductance per unit length G, Siemens per meter or mho per meter. And capacitance per unit length C, Farad per meter. So the line parameter R, L, G and C are not discrete or lumped, they are distributed. So they are not discrete, so they are distributed. What I mean to say, these parameters are distributed over the length of this transmission line. At particular one point I cannot say the resistance is this much. Okay, I need to have certain length provided of a transmission line, then only I can tell those values directly. The parameters are uniformly distributed along entire length of the line. Okay, these parameters are uniformly distributed. Let's take an example. Okay, I will just give you an example and then we will proceed. There is one impedance of the transmission line associated with it. It is called as a characteristics impedance Z0. So if I am talking about this characteristic impedance Z0, if someone asks me if Z0 is equal to 50 ohm, where this exactly value 50 ohm? 50 ohm value if I am getting of the Z0, where it is exactly situated along this length of transmission line. So at any point you take on the transmission line, the name of this parameter is characteristic impedance. So this impedance is actually giving a characteristics of this transmission line. So it is basic parameter of this transmission line, and definitely I need to see that Z0 is equal to 50 ohm is valid throughout the length of the transmission line. If I measure here, it is 50 ohm. If I measure here, 50 ohm. If I measure at this point, it is 50 ohm on this transmission line. So that's why its name is characteristic impedance, something like that. So if I'm talking about these parameters along the length, that means these parameters are distributed over the length. They are not lumped or discrete one. So this is the point which we were discussing. Then coming to the next point, for each line the conductors are characterized by, since there are two conductors running parallel to each other, they are characterized by sigma c, that is conductivity, mu c, that is permeability of a conductor, and epsilon c, permittivity of a conductor, is equal to epsilon naught, and the homogeneous dielectric separating the conductor is characterized by, because there is a medium in between these two conductors, so it's a dielectric medium which is characterized by sigma, mu and epsilon. You already know, in the boundary condition also we have gone through sigma, mu, epsilon. What is this? Conductivity, permeability and permittivity. This is for free space, and this with the suffix c you are able to see they are for conductors. Remember, there is a difference between this sigma c and this sigma. This is conductivity of a conductor, this is conductivity of the dielectric which is separating the conductor. Next point, G is not equal to 1 by R. G is a conductivity, but it is not exactly 1 by R. R is an AC resistance per unit length of a conductors. R is resistance per unit length, ohm per meter, of a conductor comprising the line, and G is the conductance per unit length due to the dielectric medium separating the conductor. Okay, so this G is of, I will take you back to this diagram. R is a resistance of this conductor, and G is a conductance between conductance of this insulating medium. So they are not directly related. Listen to me carefully once again. This resistance R is the resistance of the conductor of the transmission line, and conductance G, this conductance is of dielectric medium. So this dielectric medium and conductor, we cannot establish a relationship between them directly. So G is not equal to 1 by R, and G is the conductance per unit length due to the dielectric medium separating the conductor. The value of L is external inductance per unit length, that is L equal to L ext. The effects of the internal inductance L in equal to R by omega are negligible at high frequencies. Most communication system operates, because if I am talking about frequency and what is the impedance offered by XL, you might have written this in the first year even. XL is what? Is 2 pi FL. Is 2 pi FL. Yes or no? So inductance. So these effects of internal inductance are negligible at higher frequencies, but there these external capacitance play an important role. This capital L equal to L ext. This unit is Henry per meter. And finally, for each transmission line, this equation you must remember, everyone. Any transmission line you take, this equation holds true. LC equal to mu epsilon. LC equal to mu epsilon, because these things we require in special cases of the transmission line while solving the numerical. LC equal to mu epsilon, and G by C equal to sigma upon epsilon, and G by C is equal to sigma upon epsilon. These two things you should know. Okay, LC equal to mu epsilon and G by C equal to sigma upon epsilon. This is true for every transmission line. So this is about the line parameters of the transmission line. We will stop here. In the next lecture we will start with the general solution of the transmission line, where we will see that how general solution is described, and how mathematically expressions can be derived for the transmission line, and how they hold true for any transmission line. So till then, happy learning and thank you very much.